Hello everyone, I'm Zed. So I run a company called Ziax. We are mainly known for a brand that we have called CubeCraft, which is a Minecraft server partner brand. And this presentation is basically a bit of a story of our engineering journey over the last, well, I've been there 11 years now. I started when I was 15, so over quite a while, and what kind of goes into doing multiplayer games, some fun lessons, some hard lessons, and where we've ended up. Most people are like, what is it you actually do as a Minecraft server? And so this is literally, if you've seen Minecraft, basically if you play on the Java Edition server, or the Java Edition version of Minecraft, you can join a third-party server, which is not affiliated with Mojang or Microsoft in any way. And then once you connect, you're connecting through to our infrastructure, it's our worlds, it's our assets. You're playing with other players that we have on the game. So this is, well, another 8 people on this game, and we have a variety of game modes. And then about 8 years ago, I don't know, at some point Microsoft reached out, and then for the console editions of the game, mobile, all that kind of stuff, they wanted us as an official partner, which we said yes to, and so we're now an official kind of still modding, but kind of sit within kind of the official Microsoft ecosystem. And we have quite a lot of players. We've had over 100 million in our lifetime, and we still regularly see probably around hundreds of thousands every day, probably about 1 million weekly active users, something like that. So it's a lot of things, and a lot of infrastructure to manage that. To have tens of thousands of connected players at once requires quite a lot of infrastructure. In order to, before I go into that, I just need to give you a quick crash course on how to run a Minecraft server, so this won't take too long. Basically, your users are here at the top, and the way that most Minecraft servers work is you kind of join a layer 7 proxy, kind of like Nginx or Apache, but for Minecraft, and then we can then route you around the actual matches or the game instances or something like that. It's a bit weird, it's not how a lot of games work, but it basically means that we hold a connection to your user here, you're speaking to the same proxy, and then we can bounce you around both in the local site and all of our global sites as well. Easy enough, right? That didn't take long, but just a few Minecraft servers, it's all good, a few players. So CubeCraft at 1 million DAU, which is kind of where we poke to. Minecraft's an incredibly challenging game to scale. One of the big reasons for that is it's incredibly bandwidth and compute intense. It's probably about, on a per client connection basis, it's probably about the bandwidth of a 240p YouTube video, kind of a few megaseconds, something like that at peak. We're sending the world over the wire. If you think about a game like COD, you've downloaded all the world, all the assets, all that's kind of going on. We're actually having to transmit a lot of that, all the chunks, blocks, all that kind of stuff. It looks low fidelity, but let me tell you, the data's there. And sometimes graphic over there. And we've got PvP. We're competitive games. People care about latency. We need to make sure that our net stack is very performant. We also have a very incredibly healthy cheat ecosystem and quite a hostile cybersecurity kind of posture in gaming. We've found over the years that we'll have groups come and target us, both kind of through classic DDoSes and also more complicated, both layer 7, human engineering, all that kind of stuff. Then a couple of years later, we find them in the news doing something with a bank or being contracted by a state actor, and we're like, look how they've grown up. So we have to have a very strong security posture because it's not a compliance thing for us, it's just a business risk, like people will poke and find stuff. And then we've got all the traditional scaling problems as well. With millions of players, we've got lots of data, we've got lots of bandwidth to have, we have lots of compute, we have terabytes of RAM in production, to actually run all the game servers, and a lot of that runs exclusively on more or less exclusively on bare metal. So we have quite beefy bare metal machines all around the globe, a mixture of owned, rented, and then we do occasional bits of public cloud burst as well. So how are we going to go from this to working on Kubernetes? We're going to talk about what we did in the old days before we took on our Kubernetes journeys and how we actually ended up solving a lot of problems internally, which we realized everyone else was solving in different ways and for web applications and more traditional apps. And then we'll talk about we had quite a seminal moment within the pandemic. For gaming, that was quite intense time. Everyone was sat at home playing video games. It really pushed our legacy infrastructure to its max, and we started our kind of proper cloud-native transformation journey there. And then if I have enough time, I'm going to talk about how I built a multi-gigabit message queue on top of IRC, but I don't think I'll have time. So, but the slides are there if we get there. So homegrown software graph. Back to the mechanics of how you build a Minecraft server. So we are modders at heart. So we basically take what Microsoft makes and what Mojang make as the actual base Minecraft game, and then we mod lots of stuff of it. We patch the internals, we add extra assets, we do all sorts of kind of custom world files, and then we need that server which we build and mod to be able to connect to all of our infrastructure. We have probably about 200 game types, you know, between kind of the type of game, the match, how many players they're going to be, all that kind of stuff. And they all require a slightly different configuration. And we had quite a big problem of how do we actually orchestrate that working directory. In the same way that in a web app, you're going to have lots of different microservices and all that kind of stuff. We needed a way to kind of graph that really, because what we had in our deployment is a lot of the games would have common dependencies. So we didn't want to have duplications of 200 configuration files all with very similar things. We wanted a way to kind of graph the dependencies down. And yeah, so like actually within a Minecraft server, I'm so excited. What am I going to do? Oh yeah, so this is like, you can see basically this is a built server instance for us. You can see the kind of amount of supporting data it requires. It's got a mixture of MCA world files themselves. We've got a lot of config JSON. We have the actual jar files which contain all of the code for either the games or supporting services and stuff like that. And then back in the day, we had that all in an individual repository. We've now got it in a monorepo, but at our peak, I think we had around 300 to about 350 software components, which for a team of, at the time, was probably only about 5 or 6. It was quite a lot to manage and keep on top of and all of that. And they're all really highly coupled. So like a game would rely on the framework, rely on the libraries, rely on the server software, would rely on the Java runtime. And they were all on separate CI and CD pipelines. And we graphed it all. And this is what the graph looks like. So we actually kind of put our entire application state into a graph. You can see here these green triangles represent a type of game. The blues are the map variations, and the pink are artifacts. So that could be something out of our CI pipeline. It could be a world. It could be an art asset. And basically from here, you could go from green and resolve down, a green and blue combo, and resolve down to everything you'd need in order to build that application and start the server within the production environment. Yeah, this took a long time to render. And then basically what we had is we had an assembler. So as you booted up a Minecraft server, we'd have services which go, oh, we need a Sky Wars game or Egg Wars or a game of this type. That was run by Network Control, which was our orchestration system. Interesting word, orchestration. I wonder if that will come back up later on. And it would download the graph, resolve all the artifacts, build the workspace, and off it went. And in the original days, that was pre-containerization. It was all kind of on the same node running kind of each time. We had to build an internal CDN for all the binary and asset distributions because we were basically building fresh each time. And that was actually just on like transferring assets and the stuff. We're eating terabytes of bandwidth. To make all matters worse, Minecraft's a really weird game. We had Java edition, we had Bedrock edition, and at one point we basically ended up with 3 versions of the network we were maintaining at once. So of those 350 software components, probably 150 of those had Minecraft-specific version stuff in them, and some of them would have 12 working branches at our peak because we would have production network, development network for all 3 versions, and then we were doing a big framework migration as well at the same time. It became very, very difficult. But the graph allowed us to have very easy horizontal scalability. It allowed us to have incredible cardinality, so kind of small tweaks in an application configuration would allow us to very rapidly prototype new game modes. We could just push a role, and that would kind of scope out quite well. And we could deploy really quickly. One of the benefits is we didn't have a fat container image, which we needed to build and disassemble. If we were switching out just a JSON file, we just switch that JSON file out, the cache would purge in the internal CDN, and the change could be out within 30 seconds from a pipeline run. And that was really valuable to us in terms of fast iteration. And so yeah, kind of we had a very scrappy beginning, like stuff like the software graph and other kind of quirks we did back then allowed us to iterate incredibly fast. We built this base on kind of quite, hacked together bash scripts, massively kind of over-provisioned, originally over-provisioned and then strained database servers. We were kind of figuring out on the fly how to run, sharded Mongo clusters. We had massive MySQL databases that we were trying to keep on top of. We inherited a lot of tech debt, which is not always a bad thing, because that tech debt allowed us to grow and allowed us to be successful as a product. But it kind of started to really come apart at the seams is probably too strong, but we were definitely getting woken up a lot of the time at 4 a.m. by PagerDuty as something new would set on fire, which was not so fun, especially after a night out. So that's not great. But what I think when we were looking at kind of rebuilding our infrastructure for and going into more industry standard ways, we wanted to take a lot of the lessons that we'd learned. We had actually innovated on quite a few things that hadn't been done in the wider industry. And we do still have some constraints that weren't looked at within especially kind of less cost sensitive businesses, which frustrated us. So we wanted to get to 10 to 100 million DAU, and we wanted infrastructure, so that's daily active users. We wanted infrastructure that would support that. And so we kind of kicked it off and we were like, if we were starting from scratch, if we were greenfielding, what would we want as creators out of our tech platform? And we came up with this idea of Hug Your Creator. And we said, well, as a creator that's building games, we want to be supported by a really solid infrastructure platform. I don't want to have to worry about hardware failure. I don't have to worry about how the network's getting there. I don't need to worry about how, on the data side, how my database is managed. I just need to know that it's there, it's being backed up, and it's stable. And then for us especially, like ingest and network is so important, like doing all the work that we do on kind of, both with our providers and directly on kind of peering. I'm not going to get into it, but just kind of minimizing latency is something we spend a lot of time on. And we also realized that we had two things that we were trying to solve. We had our very specialist game problems, the actual running of those Minecraft servers, where every millisecond of the network stack counts. We want to squeeze every ounce of RAM and CPU out of the metal that we're buying because it's expensive. And we needed that to be fast and simple for our developers to iterate on. And then we realized that we also had a load of solved problems. Actually, all the stuff we were wanting to do in terms of building a data analysis platform so that we could run leaderboards and looking at how we store worlds and distributing that will actually solve problems. Like you can change some of the basics, but the primitives of what we were trying to solve were solved. They were kind of, we knew we needed microservices. We knew we needed kind of databases that were kind of much easier to operate at scale. And so we were like, well, actually for a lot of our data problems, we need to look for the industry, and then we should spend more engineering effort on where our expertise were. And so we kind of went through and we talked a bit about the game platform and what we wanted that to look like and the edge structure and how we do session termination, all that kind of stuff. And then we went and designed what kind of services and what we wanted in our data platform. And this looks much more kind of, whenever I've accidentally tripped into some enterprise's office, this looks more like the whiteboards they have and less like the chaos that I do. And we went through and we kind of classified the types of data that we were trying to handle and how we'd want that to be stored and processed. And we call that internally the Rocket platform. And basically what we wanted is we wanted that game platform, securely run our own and third-party workloads, support for both cloud and bare metal. We wanted to be able to have really good observability and metrics into that. Again, due to the nature of kind of what we do, we find kind of kernel pressures where you don't think they should exist, and suddenly you're like, oh, okay. We find all sorts of weird quirks of just running machines that hot. And then on the data platform side, we wanted that for both product reasons. We wanted to be able to do more complex data with our friends, social systems, stats and analytics, both on a product side and for the user, and also be able to store more consistent state for users, like save data and all that kind of stuff, which gets complicated when you need to do that reliably at millions of player scales. And so we went very hip at the time. We were like, let's get a little GraphQL interface. We're gonna, and this is a very kind of traditional maybe GraphQL not, but quite a kind of, you'd see this out of a consultant, GraphQL data interface, a series of services underneath it. And yeah, that'll be easy. 2 years later in a platform restart, we finally got there. And we this is quite old actually, through our GraphQL now, we probably do around 4,000 to 6,000 mutations a second on our data platform. It's gone up since I took this screenshot. And what we found when we were building that is we needed a Kubernetes distribution to build that all on, which comes onto the help. I started a Minecraft server, and now I maintain a Kubernetes distribution. For those who starting in greenfield for any cloud native technology, you'll often come across this. This is the CNCF landscape, and it's all the member projects to solve various problems. And it's incredibly overwhelming if you've not worked with any of them before. If you're wanting to do GitOps, where you're doing, best practice infrastructure as code, do you use Argo? Do you use Flux? If you're wanting to do your application definitions, should you be doing Helm chart? Should be using operator framework? They've got all these different options for doing it. And we've found ourselves in our discovery phase in quite a choice paralysis. And we then were looking around for the Kubernetes distributions, which make those decisions for you. And we came across Red Hat OpenShift, which is a very, and we also came across Rancher, and we came across Talos. So Talos is very lightweight, very like a, vanilla-y style Kubernetes. Both Rancher and Red Hat have various offerings, but are quite opinionated in how you run a Kubernetes cluster, what software you use, how you deploy it.
Did you consider vanilla Kubernetes at all?
As in raw Kubernetes, yes, we did, but I think for us it was we just wanted distribution guidance in the same way that we would never run Linux from scratch in production environment. We wanted a Debian or a Fedora or a Ubuntu, which had those you want a storage, you don't need to choose your partition layout, just run the installer, and that's what attracted us to them. Then we spoke to salespeople. That didn't go very well. And then we looked into it a bit more, and actually with OpenShift, many of you will know that you have RHEL, which is Red Hat's supported enterprise offering for Linux. You have an upstream, CentOS Stream, and then you have an upstream with Fedora. And it turns out it's the same with OpenShift as a Kubernetes distribution. They had OKD, which is the community upstream now. It was a sibling, but now is a proper upstream of being fully integrated OpenShift functionality, but totally community driven. And basically what you get in the Kubernetes distribution is a lot of opinions, which is what we really liked. So if you wanted GitOps, it was Argo CD integrated in the console. If you wanted to do storage, you had ODF, which was an opinionated deployment of RuxF. You had all these opinions which came into it. And so you get, and it manages all the way down. So you remember running on bare metal. For us, it comes with the operating system, and the way that it manages the operating system was very aligned with what we wanted in terms of cattles of servers. We have 3 digits worth of dedicated servers floating around the globe. We didn't want to be manually intervening and running Ansible playbooks and them going wrong. We really liked the immutable container operating systems that they did there. They run vanilla-ish Kubernetes. OpenShift has some weird quirks, specifically around RBAC and security, which for us was actually quite useful. And then you get all the cluster components. So you get the web console, you get the tooling around images, and then you have the kind of that opinionated catalog of operators for whether it's virtualization, AI workloads, whatever you're wanting to do. They've got quite a pre-built package on how to do that. And what ended up happening is that when we first looked into OKD, we were like, this sounds great. And then we quickly discovered that the community tooling wasn't there. And so we went and did it. So I actually co-chair the OKD working group. And one of my colleagues is also a maintainer of the OKD Orator project. So we actually saw that there was this community project out there, and we stepped up and now very active in maintaining this as a Kubernetes distribution. And some of the work we've been doing recently is specifically around that first-party catalog. It's the OKD Orators. It's a session we did a while ago. As a quick primer, kind of operators in Kubernetes, they're basically meta software which manages some of your control loops. So let's say I'm wanting to deploy a virtualization platform on my Kubernetes, something like KubeVirt. The operator will actually make sure it will interact with making sure the relevant, KMU and the virtualization dependencies are on the node, making sure that your storage can be provisioned properly and installs the relevant CRDs and resources into the cluster to allow it to happen. Sometimes they're called cluster extensions if you speak to someone in technical marketing at Red Hat. I don't know why. But it's basically built on a series of technologies called Operator Framework, which is basically the SDKs and the tools and conventions for managing operators in clusters, and they deploy into a software catalog. So this is what we've been working on a lot at work, myself and my colleague Owen, and we've got now, and we're building out this opinionated procured catalog of operators, and we're basically looking at what Red Hat provide in their product version of OpenShift, and we're using that as a basis for what we build in the community version as well. So with OpenShift, they have OpenShift Data Foundation. That is an opinionated deploy of Rook and Ceph underneath for provisioning storage in your Kubernetes cluster. We have OKD Storage, which is a very similar opinionated structure. We use a lot of the same repos and just some kind of repackaging. And packaging's back, right? If you go into the kind of old days of Linux and where distributions came out of, was you had all these kind of different software components, and getting them to build and run against each other was complicated. And so you had distributions, you had Debian, you had Fedora, and actually what used to be works on my machine is now becoming what works on my cluster. If you try deploying some of those CNCF projects on a vanilla Kubernetes cluster and try getting them to play nice with each other, that is much easier said than done. And so actually we think by reducing the integration effort, we both think it will help the adoption of OKD as a Kubernetes distribution, yay! But also provides a much better both cluster administrator and cluster developer stuff. Red Hat still maintain all of the kind of midstream and downstream. I do not have the same resources they do. I'm still kind of our platform team is still now only 5-6 people. So they're still doing a lot of engineering effort, but we're doing a lot of the packaging work that you would have, in the same way that you'd have packages in Debian who would take all these repos and get them in build scripts and building things. We're now doing that in a Kubernetes environment. And so, we maintain both the catalog of what we expose out to our installs and kind of clusters, and looking at the operator pipeline. We're wanting to get the OpenShift AI rebuilt into OKD AI, and we want to do some better automation of some of the catalog management. But we found it really interesting actually engaging in the upstream, and we're probably going to go further up. We have some performance things that we need to do in our use of Kubernetes. These are kind of the two things that we're looking on at the moment. So we're looking at how SRIOV attaches work. So you've probably heard me talk about networking a lot, but network performance is very important to us, and virtual networks for various reasons causes problems. We see incredibly high packet rates, and there is some work being done on this, but we're looking to improve kind of SRIOV behaviors for a much broader set of NICs than is currently kind of supported out there. Pardon?
What CNI you use so far?
So we will do, on our SRIOV deployments at the moment, it will be a Malta CNI. So we try and not break the opinions of OKD or OpenShift. And so we allow the standard kind of OVN Kubernetes to run for general pod-to-pod traffic. And it's only our gaming pods that we will then use Maltus to do a multi-attach. And we will then do an SRIOV virtual function onto that pod. So that pod has a a virtual slice of the actual physical NIC, and then we can start getting the performance that we require out of it. And so that's generally our mantra, is we want game traffic to flow over metal. We do quite a bit of instrumentation at protocol level, which affects MTU and performance and we need. And then the other thing we're looking at is some work around ZRAM to help improve node density. This has been going on quite a bit in Arch at the moment and a bit in Fedora, but it's basically where many of you will have heard of swap, which is where you kind of take some of the stuff that you've got in RAM and put it onto a disk. That can be quite expensive, even on NVMe drives. And so we're doing some work. It's already supported in the kernel. It's not great on the accounting for if you're doing ZRAM swapping within a C group, so effectively a Kubernetes container. And so we're trying to figure out how to kind of get that to work better. So we can basically, a container can have 6 gigabytes of physical memory allocated, but it can actually page some of that into ZRAM within that 6 gigabytes. So it could actually be thinking it's got 8 gigabytes of closer to physical memory than if it was actually swapping to disk. But complicated. So yeah, and I think like our approach really is something that I've found really good. We get involved in the tech that we're using, both outside of the Minecraft stuff, but also within the Minecraft stuff. We basically run an open source investment arm. We support a lot of open source projects and do a lot of the back office work for them. And from our journey, like that's been really important. Like in order to solve your business problems, you actually need to know your stack. Like we didn't know much about OKD and Kubernetes, so we kind of jumped in and started maintaining it, and that's how we learned so much. You learn by showing up to the working groups, by listening to Signode. And if you're just starting out in Kubernetes, like all the working groups are public. Like find something you're vaguely interested in and go help. You start writing documentation. You start with little things, and then before you know it, you're kind of got a lot of headaches. But yeah, I think for us as a business, like the open source, participating in those communities, massive return of investment. The kind of level of skill of engineer that we've got now is far beyond kind of what we is because they've been contributing in of open source community. But hacks also work. Like we still do bits and bobs which probably make anyone in financial institutions or governments cry, but we have fun with it and we get to do really cool stuff at quite big scale without breaking the bank. So yeah, and that's how I started a microserver and ended up maintaining Kubernetes distribution. Any questions?
Oh, I have questions. So you're stating that you run Kubernetes on bare metal.
Yeah.
And I have experience with running the Kubernetes both on bare metal and on virtual machine. And so what we were seeing is that if you run Kubernetes on bare metal, it gets corrupted at some points, like the Docker or Podman directory is getting corrupted, and at some point you need to restart it and clean it up in order to restore it to like the proper functionality. Did you encounter this problem, and how you are dealing it with bare metal? Because it's much easier to deal with virtual machine.
Yeah.
You just kill the virtual machine after some time and you have a new one.
I mean, so we do have like bare metal tooling which allows us to reset machines quite easily, but because of how OpenShift and OKD work, where it's immutable operating systems underneath, so basically your operating system, and in fact in the next version of OKD it will switch to bootc, so basically there's a tiny bootloader and that runs a container file as the actual node operating system, so the kernel, initRD, all that kind of stuff is inside a container file, and you can't change that at runtime. So a lot of the causes of machine and node drift are removed by using immutable operating systems. Of course, you will still have general drift within your the like the corruption of the containers. Yeah, we've not had any. We've not had that, again, mainly because I think like we're very disciplined on when we intervene. If we're fixing or debugging, we clean up after ourselves, and we've got discipline on how we intervene on nodes.
Yeah. Thank you.
Question. So some of the things that you're talking about remind me of conversations that I've had with friends about who work in the high frequency trading space.
Yeah.
Like, are you talking to people like, I don't know, Jane Street and other people who do, because they're solving, I mean, they're talking to Intel about optimizations at instruction level on CPUs to get picosecond advantages over their competitors.
Yeah. So I think we get some of the things. I think it's surprising how often gaming and high frequency trading kind of clash together, and how much more money is in high frequency trading. But so like some of the stuff around, I mean, it's slightly different. So like ZRAM's like a density thing, which in HFT you would just throw more RAM at the problem. But some of the stuff we're doing on, it's like what we're currently working on at the moment is with the SRIV attaches, is getting them to reliably do bonding which is difficult to do, kind of have your host NIC bonded as well as all of your virtual functions bonded up to the switch, and that's would probably be relevant. But no, we're not super talking to them. Like most of our interactions are kind of via Red Hat engineering. They do a lot of platform enablement. Like that's kind of the main team that we work with. But yeah, like ultimately we're not really an Intel customer, like, and we're not a Red Hat customer. Like we are just part of the community, and they probably won't just pick up the phone to me. So yeah.
One more practical issue. So, when you have bare metal servers, you usually can run really a lot of containers on it.
Yeah.
And it seems that more because like vanilla Kubernetes at least,
Yeah.
is when you have some product that you are making for Kubernetes, it is usually certified against running 100 pods. And when you run more than 100 pods on a single node, the things are starting to break because they were never tested for it. Like Datadog starts dropping logs,
Yeah.
you have more pods, etc., etc. So for that reason, at some point we decided to split the big bare metal server into virtual machines just to not exceed 100 pods per node. And
Yeah.
Did you experience similar?
I mean, we are definitely running on some of our nodes more than 100 pods and not seeing many issues. But on a lot of them, like the actual game servers are quite expensive. Like they're incredibly stateful applications that are like, we couldn't run 100 game servers on things. The size of bare metal we deploy is not mega. It's probably half a terabyte of RAM, kind of equivalent of single processor. I can't remember it's an Epic brand, but it's basically the Epic version of a 9950X 3D. So I think it's like 9544P, something like that. Yeah. Yeah. So for us, we don't get the economies out of that. So like we're relatively like run things by a shoestring. So like we found the kind of perfect bit where like the Epic, the cost per CPU we're getting is good for us, and for some of those things as well. Like, so we're quite happy with the density that we're at on those boxes.
So we've got a host of 24 terabytes of RAM and 100 pod and really nonsense with 24 terabytes of RAM per host, hundreds of hosts, no problem.
Yeah.
No, it's not about the amount of RAM, it's about pods.
Yeah, but obviously when we've got 24 terabytes of RAM, we're scaling well past 100 pods.
Unless you have 30 pods, okay.
Yeah, it's not. That's something.
But like we've not hit any, and I know like OpenShift have done works on testing ridiculous amounts of pods, and I think they've got validated kind of test cases up to tens of thousands of pods in clusters. So
I mean, it's all about pods per node. It's not per cluster. Per cluster, there's really no upper limit. But
There's definitely is an upper limit. You can stress out your etc. D cluster quite easily, but cool. Any other questions?